Earlier in this course, we explored a particular type of number, the rational number. Well, it might have occurred to you that there are numbers which are not rational. In fact, if there weren't any numbers that weren't rational, why do we even need the label rational numbers? We could just call them numbers. As it turns out, there are numbers which are not rational. And in fact, we've recently been exploring some of these. Today, we're going to be a bit more precise on defining the different types of numbers that we can work with. A very important idea in math is that of the set, which is a collection of mathematical items. Often, that will be a collection of numbers. Now, we've already worked with some of the most important number sets. The whole numbers are the numbers used for counting, including 0. The integers are the whole numbers along with their negative counterparts. And the rational numbers are the numbers which can be written as a fraction or ratio with 2 integers. We're going to add to this list 2 new number sets. The real numbers are the numbers which can be placed on the number line. And the irrational numbers are the real numbers which are not rational. Now, in case you were wondering, are there any numbers that are not real numbers? That is, numbers that can't be placed on the number line. Well, as it happens, there are numbers that can't be placed on a number line, but those take a little more to understand, so you'll have an opportunity to discover those in high school. Rational and irrational numbers. We've already seen that integers, terminating decimals, and repeating decimals can all be written as fractions using integers, so they are always rational numbers. In fact, every rational number is one of these 3. Therefore, any other number that's not an integer, terminating decimal, or repeating decimal must be an irrational number. So a decimal which doesn't terminate and doesn't repeat is irrational. Now, in our last lesson, we discovered some numbers which fit this definition, that don't terminate and don't repeat. In fact, the square root of a whole number, which is not a perfect square, is irrational. Now, another number which is irrational is pi, or the ratio between the diameter and circumference of a circle, whose digits start with 3.14159. If you've forgotten about pi or haven't learned about this yet, that's okay. We don't need to understand its purpose here today. The main thing to know is that it's irrational. Combining rational and irrational numbers. So we know that the real numbers can be either rational or irrational. What we're particularly interested in now is what happens when we combine different rational and irrational numbers. So here are some important results. Firstly, the sum or product of 2 rational numbers is always rational. The reason we know this is true is that if 2 numbers are rational, that means they can be represented as fractions. Now, if you add 2 fractions, you also make a fraction, and if you multiply 2 fractions, that also makes a fraction. So, the sum or product is always a fraction or always rational. Another way of describing this is to say that the rational numbers are closed under addition and multiplication. Just like you can't leave a room if it is closed, we can't leave the closed rational numbers by adding or multiplying. Now, the same result is not true for the irrational numbers. So the sum or product of 2 irrationals is sometimes irrational, but not always. And we can show this through a couple of examples. So if we want to think of a pair of irrational numbers whose sum is rational, we can use the example, the square root of 5 and the negative square root of 5. Because if we add these 2 numbers together, we get 0, which is rational. If we want to think of a pair of irrational numbers whose product is rational, we could use, for example, the square root of 3 and the square root of 12. Because if we multiply these square roots, we get the square root of 36, which is equal to 6, which is a rational number. This means the irrational numbers are not closed under addition or multiplication, because we can leave the set of irrational numbers just by adding or multiplying irrational numbers. Now we're going to state a couple of other important results, but without explanation or proof, because we're going to leave proving that these are true as an exercise for the future. So the sum of a rational and an irrational number, that is, we're adding a rational number and an irrational number, the result is always irrational. And the product of a non-zero rational number, so this doesn't work if our rational number is 0, and an irrational number is always irrational. Now, an important skill in math is taking statements that we know are true and using them to decide if other statements are true or false. So we're going to practice that here. So consider the following statement. The product of a rational number and a rational number is never irrational. Well, one of our earlier statements said that the sum or product of two rational numbers is always rational, and irrational is the opposite of rational. So this is true because the product is always rational. Our next statement is 3 plus pi is a rational number. Well, this is false because 3 is rational and pi is irrational. And according to our statement above, the sum of a rational and irrational number is irrational. And our final statement, 2/3 times the square root of 25 is irrational because it is a product of a non-zero rational number and a square root. This one is false because though the square root of 25 is indeed a square root, 25 is a perfect square, so this equals 5, which is rational. This is the product of two rational numbers, so the product is rational.